Let's do two review problems here, one on electric flux and then another one on determining potential. We have a square loop, side length L, and the electric field is not constant throughout. It varies according to this equation right here, where alpha is a positive constant. Now, what would the unit on alpha be? We know that the unit for electric field is newtons per coulomb. That has to equal whatever the unit for alpha is multiplied by the unit for x squared, which is going to be meters squared. What would those units have to be? We would need newtons in the numerator, we would need coulombs in the denominator, and we would need meters squared in the denominator. Now, let's determine the magnitude of the electric flux. Electric flux is going to be the electric field multiplied by dA. And we have to do an integral here because the electric field is not constant, but varies according to that equation that was at the top of the page. Let's see what we've got here. The electric field, we're going to integrate this from x equals 0 all the way to x equals L, because this is a square. So as we go to the right here, we're eventually going to reach a length of L. And the electric field, we're told, is equal to alpha times x squared. So that's what E is. And then what's dA? Well, dA is this little thin slice here where the electric field is constant for every bit of that slice. And dA has a height of L and a width of dx. When we pull the constants outside here, we're going to get alpha is a constant and L is a constant. So we're going to need to integrate this from 0 to L x squared dx. And when we do that, we're going to get alpha times L 1/3 x cubed. There are our limits of integration. And when we solve this, I think we're going to get 1/3 alpha L to the 4th. That's the expression for the electric flux through that loop. Let's move ahead to a problem where we do an integral to figure out what the potential is. First of all, this potential is going to be a positive number right here because this line of charge is positive. And in general, you remember that when we find a potential due to a point charge, it's equal to K, I'm leaving a little space here, Q over R. But each little dq is not the same distance away from P. So what we need is the dV contribution, and that's going to be equal to K dq divided by R, and we're going to have to add all those up. How are we going to do that? Well, let's see. What is dq equal to? It looks to me like dq relative to dr is the same as q relative to L. So that means that dq is going to be Q over L times dr. If we want the total potential, we're going to have to sum up all of these little potentials from R equals A to R equals A plus L, K Q over L, dr over R. K, Q, and L are constants, so we can forget those. Well, not forget them with regard to integrating. We can put them out front, and we end up integrating dr over R. Well, that's just the natural log of R. If we continue the calculus here, we're going to get K big Q divided by L times the natural log of R with the limits A to A plus L. I think we've reached the end of the road here. KQ divided by L times the natural log of the quantity A plus L over A. That's the magnitude of that potential right there, and that will be a positive number.